So you guys, part two, we're moving away from, let me jump back to do a quick summary. We talked a lot about voltage. So if we're going to do our diagnosis with voltage, right, you'd be thinking the source, let's say, is 12.6 volts. You'd be tracing this and you'd say, well, going into the switch, I'd expect like a 12.6. Coming out of the switch, assuming it's closed, I'd expect maybe 12.6, but by then it might be 12.5, right? So we've been doing a lot with voltage. So just to remind you, we can do a lot of our diagnosis with voltage measurements. And in a way, voltage measurements are actually the best because we test it while the circuit's live, the circuit's active. That's kind of like the summary of the last one was, some of you may have seen it. I think, who had the fuse that was kind of burned? You and Gregorio, you had a couple different ones. I know Gregorio had one of them. I think it was Priscilla, right?
Yeah. We had a fuse that was...
Okay, it was totally blown. Yeah. One group had a very interesting fuse. So this doesn't even have a fuse in the circuit, but this fuse, if you pulled it out and you looked in the light, it looked like it was okay. And then if you tested it with the meter on ohms, it was okay. But then when you hooked it into the circuit, if the switch was open, it would measure like 12.6 in and 12.6 out, which means the fuse is good, right? But by the time you close the fuse and it actually put some load on the system where it was trying to light the light bulb, there was actual current flow. That fuse was like it was really blown, but it was like just connected by just the tiniest little hanging by a thread. And with the system on, it would actually show 12.6 coming in and a 0 coming out. So it's a little bit weird to understand, but the best way to test the full integrity of the circuit is to do the voltage. All right, so that was really what we covered last week. That's the best. But there's some cases where you can't do that, and other cases where we want to test other things. And so we need to talk about the three different properties of electrical and how you measure them. Remember, volts is like the electrical pressure last week, big time. Current is like, how would you describe current? If it's not the electrical pressure, but like more like the volume of the flow. Yeah, exactly, the flow. And then the resistance, that's that last one that's in ohms. That's kind of like the resistance to the flow, right? So if you're, the customer doesn't typically come in our business and say, I want to know how much current's flowing through this particular circuit. They don't request that. That's not realistic. Now, in a little bit of automotive related, let's just say you want to put those big LED lights on there. You want to put all sorts of lights from Baja Designs or from whatever. And if you're about to do that, you need to know how many amps those lights are going to draw. And that way you can know what size wire you need to use. And that way you can figure out what size fuse you should use and have it all safe. But see how that's kind of more like engineering? And you can do a little bit of, how would I say, redneck engineering if you want to. And you can put your own lights on, and that's, that's common. But mainly our focus is repairing the vehicle, which means the engineers already designed the circuits. All we're trying to do is figure out what's wrong with the circuit. And 90-something% of the time, we're going to do that with volts. Cool. Volts tells you a lot. Tells you just about everything you need to know. But there's once in a while, let's say a customer has a fuse that blows. You may need to really measure the amps to determine how many amps are flowing. Like if the fuse blows because of a dead short, you can probably actually figure it out a couple different ways. But if it's something more like it's a 10 amp fuse and it might blow like you put a new fuse in and it might last an hour, a day, a week, or whatever, you'd be like, is this thing intermittently shorting out? Or is this thing just drawing like so many amps it's kind of close to blowing the 10 amp fuse? I don't know. The only way we would know is if we were to measure it. So if your fuse is intermittently blowing and you go ahead and you measure the amps and the amps on the system are 4 amps, do you think the 4 amps is blowing the 10 amp fuse?
No.
No, I agree. So that means sometime at some point intermittently, it must be spiking to over 10 amps, right? So at that point, you're looking more for like maybe a harness that's rubbing and shorting on a piece of metal, that would make a short and that would blow it. Whereas if you were to do, like I had one story I mentioned to you, I had, it was actually a motorcycle, but the way a fuel injected motorcycle works, same as a car. It's got a fuel pump that's powered by the battery. So like if we were to look back here, a little bit further. So like here's your battery. That battery would go through a switch, and then if your fuel pump was over here, the fuel pump gets the 12 volts in the ground. What was interesting is the fuse for the fuel pump would intermittently blow, but what was strange is this is on my own motorcycle, so I got not only the picture of how to diagnose it, but I also got the picture of what it looks like from the customer, because in this case I'm the customer too. What was weird about this one, if I were to start the bike, the fuse may or may not blow. But if the bike were already running, the fuse would never blow while I was riding. Is that weird or what? It would only blow maybe like 1 out of 10 times only on initial startup. It was the strangest thing. So if it's only blowing on initial startup, it's not when I hit a bump, it's not when, you know, I give it too much throttle or something. I was thinking about it. That doesn't sound like a harness that's shorting out or anything. So I'll make this a long, extensive diagnosis kind of short. What was happening with that fuel pump when I measured the amps, it's a 15 amp circuit, and the thing would be drawing like 14 amps. That's too close. It's like when I would initially start it up, sometimes it might even draw more than 14 amps on the initial startup. But once it was running, the amps would drop to like 10, you know, or 9. So 9 is good, that's not gonna blow a 15 amp fuse. 10 is good, it's not gonna blow a 15 amp fuse. But 14 is like, it's too close already. So measuring the amps kind of gave me a picture of, I'm not really chasing an intermittent short. I'm chasing something that's making this fuel pump draw too many amps. Kind of makes sense? See how I'm kind of diagnosing this? Now the worst part about it, that fuse would blow maybe twice a month. So like the diagnosis is really tough. I would put a new fuse in and it would work. And it would work tomorrow and the next day, the next day, the next day. And then 2 weeks later, I'd go to jump on it and I'd go to crank it and it would just I know it blew the fuel pump fuse again, so I'd have to get off, take the seat off, go into my little bag, get a little fuse, pull this fuse out, put the new fuse in, and then boom, it would start up and I could go for like another 1, 2, 3 weeks. Cool. You know, that's a problem that's bad enough where you could get rid of the vehicle for that type of problem. That's a hassle. But think about it from the technician standpoint. You drop it off at the shop, boom, here you go. Fix my intermittent no start problem, electrical problem that intermittently blows a fuse. Like, what do? You say, well, let me keep trying it every day for 1 or 2 or 3 weeks. You know, just think about that for a second. You're gonna check it every day for potentially up to 3 weeks. What kind of money you want to charge for that? Working on this car for 15 minutes a day for 3 weeks straight. That's a lot of money. So that's not a real practical diagnosis. The practical diagnosis is to understand the electrical circuit, right? So voltage is one thing, and voltage is 90% of what we do. But like in this case, when I have a fuse that's intermittently failing, I need to get a kind of a better picture. So when I see it's drawing 14 amps on initial startup, I'm like, that's too high. You know what's pretty common to cause a fuel pump to draw too many amps? A problem with the pump. So right there, I'm like, if this thing's drawing 14 amps, especially when it first starts, I'm putting a fuel pump in it. I'm not putting a harness. I'm not trying to find a chafed wire. You see what I'm saying? So like I already got a better picture of the system. Measuring amps can tell us stuff. It's just not the most common measurement that we do. Cool? So we'll get a little bit more into detail. So if you want to just measure amps, generally on the vehicle, we're dealing with DC, right? So if we're measuring a direct current system, you're going to set it on DC amps. If you have your meter set to AC amps, guess what? It's not going to measure anything. It's looking for alternating current amps, not going to measure it. And then this is what's kind of different. We have to move the red lead to the A socket. In this case, it's a big A. It's a uppercase A. Remember that one from last week? That's the one that's fused. Okay, so hold right there. Right here, this one says 10 amp max, it's fused. Cool? Because remember, when we measure the amps, we have to actually send the electricity through the meter. And if you're going to send 8 amps or 9 amps through the meter, the 10 amps big A port is fine. It's happy with that. No problem. But if you were to leave it on the little a, see this one? It says MA. You guys remember that from last week. The little m is milli. So if you want to measure milliamps, cool. This port's good for milliamps. But look, it's fused to 400 milliamps. So that's like 0.4 amps if you do the whole calculation that we did last week. That's going to blow instantly. You're going to be like, let me measure this, poof. Let me put the fuse in, poof, right? You have, move it. You got to move it. Okay, makes sense? Now we'll come back. All right, and then if it's a manual range DVOM, you got to select the range, but we had quite a conversation about auto ranging and manual ranging. Generally, the go-to is going to be the auto range. You just have to pay attention if it has a little m or, you know, the prefix they call that, okay? And then one thing you could do is you could start with the highest range, and if you don't really see anything, you can move it down and move it down and move it down. You just don't want to move it down too far. If you move the manual range down too far, did you guys catch what happens? It's not scary, but something comes up on the screen that's no longer helpful. If you, oh well, exactly. So that's your add a limit or over limit or, you know, these types of things. So let's say that you have it on a range of 4 amps and the circuit is drawing 8 amps. It's not going to read 4 amps. It's going to read OL. So you can, you know, move it up. Cool. And then let's just say generally when we're measuring amps, we're talking about using just the meter. We need to actually measure it in series. So we need to put this into series, and we're going to get a little bit more into that. That's a critical point. So if I'm once again going to play meter leads right here, and let's just say this was still connected and I didn't break open the circuit. You see right there, we've broken open the circuit. But if I were to just take my meter leads and go here, boom, now you'd see current could flow this way, but current would also flow this way. If you think about it, if I make the current flow this way, I'm giving it an alternative path. That would be, if I don't open the circuit, I basically add a parallel circuit. I add a parallel leg. The problem with that is, remember, when we're in the big A port, this has very, very little internal resistance. So if I set it up like a parallel circuit with very little internal resistance, what do you think that means? I'm even going to draw it to make sure I'm thorough. You look at this. First off, let's focus in. Actually, we're going to go a little inside of that. We don't really care about the switch side of the relay. Let's focus in right in here for now. Where is the load in that circuit? We covered that first. That's why we covered it first, by the way. What is the load for this electrical circuit?
The horn?
The horn's not in the box though. I agree. Over here, this is the load, but in this part, this is the control side of the relay. Right there, yes. This right here. How about if I draw it like that? Does that look like a load now? All right. What if this stayed closed right here? I never broke open the circuit because I forgot. Remember I told you the senior tech who took my meter and blew the fuse for me? Nice guy. Well, here's what he did. He's like, oh yeah, let me measure amps of the circuit. And he took it like this, boom. Now look at what I just did. If this is still closed, this has 12 volts, right? Volts are going to come down, and they're going to be like, oh, let's go. In fact, this one might not make tons of sense. Let's say that they move this down here, actually. This would cause the problem. If we put it right there. 12 electrons, we'll just say. Electrons will come down and they'll be like, I'm supposed to go through this load, but rather than go through that load, you know what I'll do? I'll go into the meter and out of the meter because the meter has zero resistance inside, essentially. Cool? So if I do that, yeah, the load's here, but basically I would have bypassed the load. So that would be a short. You understand? That's a short. If you allow the electrons to bypass the load, that's a short. You basically just took your positive and you connected it right to the ground. You know, that's when sparks fly and stuff because there's an unlimited supply of current. There's no resistance in the circuit. Remember we talked about, like, you remember that picture, right? The guy, the ohm is pulling up on the rope. Remember that one? What if the ohm guy just like let the rope go, checked out and just walked away? You'd have a whole bunch of amps flowing through there and it would actually blow the fuse. What fuse would it blow? Well, hopefully this one, but possibly this one. Makes sense? So that's what the more senior tech did wrong. He was just a little rusty. This could happen to all of you. This could happen to me. If you're not constantly measuring amps, right? Because I told you in my approximation, 90, maybe more % of the time, we're measuring volts and voltage drop. We can do so much of our diagnosis like that. Then once in a while, you got a problem like the example I gave you, the intermittent blowing fuse, where you're like, let me measure the amps. And then you put it on amps and you move it to the big A port, and then you're like, pow, I don't know, somehow the meter no longer works, right? Because you forgot what you have to do. You have to open up the circuit. Now the current flow is going to go from the battery, through the meter, out the meter, still through the load. Cool? If you didn't break it open, you literally shorted it. But if you break it open, you're still having the electrons go everywhere they used to have to go. You just made them go through the meter along the way. Kind of makes sense? So you'll recall the function of the meter in this situation is to count electrons. Every electron that goes by has to go through the meter, and the meter counts them. I don't remember the number, how many millions or billions of electrons equal 1 amp, but it counts them. Count. Okay, makes sense. That's what you got to do. If you don't do that, you're going to blow the fuse. Don't ask me how I know. I already told you. Cool? And then at this point, remember, we're measuring the amps on this part of the circuit. If you want to measure the amps that's actually on the horn side of the circuit, then no problem, but you got to do your measurement over here, which would mean you need to break open the circuit over here. Okay, just so you know, this circuit got a little bit more complicated just because it had a relay in it. So there's kind of two parts to this circuit. Cool. All right, so let's just say, we'll do some exercises. You'd be a little bit surprised, but if we have a 12 volt battery and we have our amp meter here, our amp meter here, and our amp meter here, this seems like it's going to be kind of complicated, but I'll show you just how simple this is. All right, so first off, we're going to use the DVOM when taking DC current measurements. Circuit must be broken in two. Remember that? It must be broken in two. I explained why. And the end of the ammeter connected to one of the two broken ends. So if we break the circuit open, we're going to basically insert the meter like this, and the electrons are going to go through the meter. That essentially looks like this. You see the A1? The A1 looks like it's a load or something, but it's really not. It's just where we've inserted the meter. The red lead is connected here. The black lead is connected here. You see red and black? Kind of makes sense. And then we could do a quick prediction. Let me check something. Yeah, okay. Let's do a quick prediction. Let's see if you've started to understand some things. We've got 12 volts. We've got a couple resistors here. Do you see R1 is 4 ohms? R2 is 2 ohms. So right there, you should actually be able to tell how many amps at A1, A2, and A3. So I'm going to give you a minute to think about this. Then I'm going to start to help you a little bit. I'm not going to say. I won't say. Not yet. But what I will say is we can you remember we spent a lot of times in Ohm's law, remember the thing? It looked like It looked like this. Ready? I'll draw it right here. Let's see if I can hang this out of the way.
You can slide one of those things on the side there.
Okay, do you remember this? Anybody remember what goes on the top?
B,
V. How about here?
A, no.
A's right. You could do it like that. E, I, R, whatever. But your volts is how many?
12.
I agree. What else do we know?
The resistance is 4, so it'll be 8.
Okay, close. But we actually need to know the whole resistance. So it's 4 plus
6.
So it's actually 6. All right, so if we covered this up, it's going to be this divided by this, right? And that's why we did Ohm's law. You're the engineer. You're not going to be the engineers. So we don't really super commonly do this math, but you do need to know the theory so that you can have an understanding. And right now we're about to predict. If I looked at this, I had 12 volts and I had 6 ohms. My amps should be 12 divided by 6 is what? 2. So we think our amp should be 2. Cool. But where? 2 here, 2 here, or 2 here? All right. Let's think about this. This is a single lane highway. We're trying to measure current flow of cars. If it's a single lane highway, all the cars are going to go the same speed. Make sense? So like, you can't be like, I'm at the back of the line and I'm going to go faster than everybody. There's only one lane. You can't get around them. Make sense? So this is the way I look at it. If it's in series like this, guess what? The amps are going to be the same, the same, the same. That's drastically different than the volts. Remember? The voltage is going to start out as a 12 or a source, right? And then you're going to drop something, and then you're going to drop something again because you're going to share the voltage. See? So you see how amps is so different? Amps is a measurement of how many cars went by. 1, 2, 3, 4. And by our calculation, we think it's going to be 2 amps. You think that's correct? It's Ohm's law. I mean, all right, so here we go. Here's the breakdown. So if you wanted to measure the voltage, V1, if you wanted to measure the voltage, that's one thing. Wait a minute, did I give the wrong thing? I'm pretty sure I don't have this out of order here. There we go. There we go. I just inserted the wrong one. So look, if you have 12 volts and 6 ohms, you do the math, it comes up with 2 amps. A1 is 2 amps. A2 is 2 amps. And yeah, you guessed it. A3 is going to be 2 amps right there. So that was the answer sheet. 2 amps, 2 amps, 2 amps. It's all the same. Kind of crazy, huh? The voltage, very different. And that's what that in-between breakdown was about. So if you were looking at voltage, you'd start with 12. Right here, you'd actually drop to 8, and then on this next one you drop to. So if this were to consume 8, I think this one would consume 4, right? So you'd have like 12 volts, it would consume 8 volts, so that would drop it to 4, and then this one would consume the 4 to drop it to 0. That's voltage, and voltage is really more valuable to understand, but amps is much more simple, right? 2 amps, the whole thing, it's all the same. Okay, you like it? Doesn't matter if you like it or not, it's still the truth. So there you go. And now let's come back to this current measurement. I do want you guys to do this, and it won't take tons of time, but for right now, let's discuss what you're about to measure. Do you guys recognize this circuit?
Yes.
It looks kind of similar, kind of familiar. You're building the same circuit as last week with voltage, except what are you going to measure? Exactly. So before I cut you loose into blowing fuses, how are we going to measure the current at point A?
You put it in the
Big A.
that, and then you put it in the black, I think. The positive.
Okay. So if we were to jump back to here. Okay. So the black lead goes here. The red lead goes
To DC.
The big
here.
Oh.
And the switch goes
A.
So right here we have milliamps, amps, or microamps, but we're looking at amps, right? So we would point it right there, okay? So far, so good. But where do my meter leads go, though? Because that's the one I'm worried about for you.
The red goes to the A, and the black goes to the B.
Boom! You just blew the meter. You just blew the fuse. Actually, in this case, let me think about that. You wouldn't in this case. That would really only happen if you bypassed the load. All right. But that would not, you would measure, you wouldn't get a real amperage reading. Remember, if you want to measure the amps in this circuit as it flows, it needs to be forced to go through everything. And we need to, remember that term, break it open and make it go through the meter along the way. So if I were to put it like this, look at my body. Didn't I just add like a different random path? I'm not making the electrons flow the way that they're supposed to. So if I want to measure A, I would disconnect the wire for A, move it off to the side. I'd connect to the wire like this, ready? Move this wire over here. I'd connect here, and this becomes my meter, like this. And we're going to put on A, and we're going to put the meter lead down here like this. Remember, you send the big A, and we'd send it over. And then the black lead has got to go like this, and you got to go. And it would actually have to go like this. See, so this would be gone, and we have to interrupt the flow and send the amps in and out, like in and out. Cool? So you have to disconnect it and send them in and out, okay? Same with B, same with C, D, E, and F. To be honest, that's kind of redundant. It's not really all that valuable to measure all those. But you guys feel like you're ready to do this? Because I want you to do it.
So after test A, then I'll take out test B.
Okay, so let's measure test B. Ready? I would keep my meter here, like this. Okay, and then for B, this is I think red, right? I would disconnect it from here. I would pull it over here like this, just get it disconnected like that. I would put my red one here, send it here, put my black one here, send it here, and this would be gone. Cool? So now the electrons are like, oh, just got to go a slight detour, but then they continue along their way.
Okay, so then,
cool, you get me?
So then I would pull off, no, I get it.
Right here, that's one. So that's what's...
See the repetitive thing.
Yeah, you just, if you want to test at B, you need to disconnect B and send it through the meter and connect it back at where B was.
Okay.
Cool, you think, we're going to do it on the board. You think you're ready for that? All right, pause me and we'll set up some boards. You ready? You get early exercise.
Okay.
In a shocking turn of events, you guys went to do these experiments, and your meter, when you set it up in series, all of a sudden it measured 0 amps and the light bulb didn't light. So we suspect the fuses are blown, but let me show you how to test. All right, this meter, we're going to set this meter up to be an ohm meter. I'm going to move the lead back over to where we measure volts and ohms and stuff, okay? Then I'm going to put this one on ohms so you guys can see. Let me know if you can see this number. If you can't see, get in a spot where you can see, if you want to see. All right, you guys see this has 0 ohms? But look, I just did the test like this. So I know that this meter can measure continuity or ohms accurately. This was the test. Cool? This is the meter we believe has the blown fuse. So I set this one up where the lead is in the A. I set this to A. And then if you'll recall, I should be able to, this should have very little to no resistance through the meter, right? Because when it's in the big A spot, it shouldn't have a lot of resistance. Okay, so I'm going to measure the resistance. It doesn't really matter which color to which color, right? But I'm going to measure it like this. You need 2 meters to do this. This meter is reading resistance. How much resistance does this meter have? Can you tell? It's OL. It's OL. You know what that means? Yeah. This meter is open internally. Yeah. So how did this meter get open internally?
The fuse blown.
Okay, how did the fuse blow though?
By bypassing the...
So,
switch the red lead to the amp.
I think probably what happened was like what we were talking about. They probably moved the lead to A, and then they probably measured like voltage drop. If you measure it like you're measuring voltage drop, poof, you bypass the load, it blows the fuse, and then you know what you do when you're a student? You're like, let me get a new meter. This meter is broken. You broke it. You're fired. Okay, so we went ahead and we took one of them apart to replace the fuse. Now remember, these fuses can be $10. This looks maybe like slightly different than the Fluke. So maybe these are cheaper. I'm not exactly sure. And Ronnie, I don't even want to know which one's bad because I'm going to show you the other way to measure it right now. So same thing, we put on resistance, which is going to be one of the things we're going to measure. Now, if I want to measure this fuse, I'm just going to measure end to end on the fuse. See that fuse says OL? So that fuse is shot. Your meter came with a new fuse. That's kind of nice. This fuse is shot, so we're just going to hide it. And this one, see how we're getting a number there? I'm struggling to hold it, but 0.2, could you see that?
Yeah.
Priscilla? Okay. So this is part of the reason I don't want you guys just be dummies who just look at fuses. Look at what you see. You can't see an element in here. You have to be able to measure it. This one's OL. This one was 0.02 ohms or so. So this one is going to go in place. But to do this, you got to disassemble the meter and pull the screws. And, so this.
That other one be bad too?
We could check. You know what? We could check both just to be thorough. I like what you're saying. This fuse is usually smaller. This is usually the one for milliamps. This one's passing. I got 0.09 ohms. I've got now with the new fuse, 0.000 ohms. So no, just one fuse was bad. And your meter was brand new. But you never know. Amazon stuff, somebody blew the fuse and then said it didn't work and sent it back to Amazon or something. I will get you a fuse though, just in case you blew it here in the class experiment. It's nice you guys bring your own meters, but I don't want you having to pay for stuff. So now does everybody kind of understand how to check the fuse? You need 1 meter to measure the other meter. 1 meter on ohms will measure the other meter on amps, and it should have good continuity, not OL or something like that.
So there's a pretty cool bunch.
There's a bunch of them blown.
Yeah, 'cause mine myself, I checked like about 4 of them, and they were
Blown, and blown.
Do we
Yep.
have enough fuses to replace all of them?
I don't know I have no idea. Usually, remember, I don't like to share stuff. I told you some things that I was really honest about. Now you see why. It's hard to share stuff because you come to it and it's broken. And then you're like, let me get a few. I don't know if we have fuses. If we have fuses, we'll put fuses in all these meters. If we don't have fuses, we got to order fuses. And now we can't use our meter until we fix our meter. And that's why I don't like to share stuff. Okay? Now pause me. All right, so we'll do the walkthrough with you. Right now, this was the circuit working. So you see the bulb works. All right, now show me how you measure amps. Okay, so you broke it open between the fuse and the switch. That's good. All right, 0.338 amps. Okay, makes sense, so let's trace it. Source comes in through the fuse into the meter. This meter's good. Sends it out and goes right along line with everywhere it used to be. All right, so that's in one spot. What if you measure amps after the load? Show me if you could do that.
After the roll, right?
Yeah. But see, I could tell you got it because you're breaking it open, and that's what you need to do. And you know it's working because as soon as the light bulb lights, you got it. Okay? Yeah, that's how you measure it. Now let's do one more experiment. Let's swap out this bulb with a different bulb and let's see if it pulls different amps. All right, so we put a bigger bulb in there. Any predictions?
Probably more.
I think so. Bigger bulb, more light, probably gonna be more amps. Uh-oh. Maybe no good. Yep. So you did a quick troubleshooting there. Oh, was the switch off? Yeah, so that bulb is no good, huh? Well, I'll switch it with one more bulb. We'll come back to doing diagnosis on that bulb later. The best way to diagnose would be voltage, but for now we're not worried about that. Check it first. Oh, you know what? Let's bypass that switch. You know how to bypass the switch?
This one?
Yeah, just jump that one right to there. No, we got another. Is this powered on?
Yeah.
Uh-oh. This one's got some issues. Unbelievable.
Is it possible that the fuse is blown?
Well, they had the small bulb working, so I don't think so. All right, now we got it. Let's measure amps. So you go break it open just like that. Intercept it. All right, so what's that one pulling? Over 2 amps. So the other one was 1/3 of an amp, and this one's 2 amps. Much more amps. Kind of makes sense because it's much more light. All right, good experiment. Let's continue. Meet you in the classroom. All right, that was kind of fun. Didn't go exactly as planned, but sometimes that's how it works. So like Mason made a good point. He took a high school class and they showed you how to measure amps, but they never showed you what to do if the measurement doesn't come through on the meter, how to check the meter, how to fix the meter. Because trust me, if you loan your meter out, somebody's going to blow the fuse for you. You might even do it yourself, but we'd never admit to that. All right, so now you guys got it. Anywhere in the circuit, the amps should be the same because this is one of the laws of a series circuit. One of the things that we cover a bit later is all about diagnosing a series circuit. Kind of makes sense? So if you want to know the amps in a series circuit, whatever, pick a spot, open it up, send it through the meter, you're good. Do not take your meter and bypass the load because that'll give very high amps because there's very low resistance. Now you know the resistance of the meter is like 0.001 or something. That's if you have that bypassing the load, the current will go around the load through the meter with no resistance and pow, blow the fuse. Cool. Another thing that could be a little tricky, those auto ranging meters. We got a couple different numbers there. So with the small light bulbs, sometimes we'll call it the peanut bulb, like the 194 bulb. That will usually draw about 1/4 of an amp. So 1/4 of an amp is pretty easy to understand to me, but the way it shows it, it could show it 2 ways. It could show it like this, like a 0.250A. Cool. That's what makes me think 1/4 of an amp. But the other way it could show it as a 250.0 milliamps. Which is bigger? That's the same number. That's the same number. And so for that reason, I want to just touch base on something. You'll see there's going to be some review, making sure you know how to do this stuff. You know what? I should probably keep this up so we can do this together. Let's do some practice. Similar last time. If we have 9,416 milliamps, how many amps is that? Do you guys remember how to do that? 9,000 to amps. 941.6. Okay, but how did you know? So that's when we do this thing. Okay. So this is amps to milliamps. You'd move the decimal 3 to the right to go to milliamps, but we're going from milliamps to amps, so it's like this. 1, 2, 3, right? So we take this. 1, 2, 3.
It'd be 9.416.
Exactly. Totally agree. So give me 90 milliamps to amps.
0.09.
Exactly. So it's 0.9. And you could even do a 0 too. Okay, 6.3 amps to milliamps.
6,300.
Yeah, because this is when it's got to go 3 digits to the right, because you're going from amps to milliamps, from bigger to smaller. In other words, you're making dollars into pennies. So if you hand me $1, it's technically not dollars, it's like $10. If you hand me $10 and you want to make it into pennies, I'm going to give you a lot more pennies than dollars, right? So you're going to go like this. 3, so 6, 3, 0. But what comes after that? Another 0. 6,300 is correct. How about 0.78 amps to milliamps?
780.
Okay, so 780. Cool. Makes sense? Because we'd have to add the zeros in here. Yep. Okay, so just keep that in mind because your meter will, your meter can confuse you. But if you keep these things in mind and you do the right process, measuring amps is not a real big deal. And who had the amp clamp? Refugio, you had that? You got it on you?
It's right there.
Let me have that thing. Right here, right here. This wasn't actually part of my lesson, but I heard you guys talking about it, so I'll preview this. We did discuss this a little bit, but this is another way to measure amps. With an inductive clamp, you don't actually have to break the circuit open. You have to...
Doesn't the car have to be running though?
Clamp it. If you want to measure amps, you always have to have the load active. So it depends on what you're measuring. If you're trying to measure that, remember the little bulb we measured?
Yeah.
If that's a license plate light, you just have to have the license plate on, the license plate light on, which means like parking lights or headlights on. But if you wanted to measure the amps with this, you could put the circuit through here. And one of the things that that comes next is what's interesting. When there's a current flow through a wire, it actually causes a magnetic field. If we can measure the force of that magnetic field, there's a relationship. Magnetic field to amps is proportional. The more amps, the more a magnetic field. The less amps, the less of a magnetic field. So this is a little bit unplanned, but I think very relevant. To understand electricity, you have to just understand this happens. And then to tie it into what we just did, if you want to measure amps, you can do it with this. You don't have to break it open. You just literally put it around the wire. Boom. It's not the most accurate. So what we were doing right there, 1/4 of an amp, we could do an experiment later and see if this reads 1/4 of an amp. It probably won't. This is more made to measure like amps, not milliamps, not really like 1/4 of an amp. It's probably not going to be all that close. Whereas the meter is going to be very accurate when we send it through the meter.
So
Make sense?
That's basically for like custom work, like custom wiring, but like.
Not really. Like the way, let's say that our main concern.
What in the car right now can I use that for?
You give me a chance, I'm going to explain it to you. I like your excitement though. Okay, let's say we want to know if an alternator is charging at full capacity. What's the alternator's rating? 100 amps. Well, you'd turn on all the loads you can and you'd clamp this around the wire on the alternator and you'd see just how many amps the alternator can put out. There's a slightly better way to do that.
Battery to the alternator.
Right, coming that big positive lead right off of the alternator, that big one. So this is good to measure a lot of amps. In fact, if you think of all the experience we just did, this is going to be very useful to us because remember back here, we could measure, with the meter, it's fused 10 amps, right? So what if you want to test a circuit that's 30 amps? You can't do it traditionally with your meter. Your meter is fused to 10, so you can't measure 30. Make sense? That's where you get into using this is going to be more helpful, and this becomes a little more accurate. Like if you're trying to measure milliamps, for an example, 10 milliamps to 30 milliamps to 70 milliamps is a very tiny difference. This is not that precise, so not helpful for milliamps. The meter would be great for milliamps, but once you're into measuring 30, 40, 50, 100 amps, who cares if it's 100 amps or 101 amps? Like it's kind of the same thing. It's kind of similar. Cool, so this is going to be helpful. You literally would put it around the wire just like that. If it was the alternator test, which by the way, that's a later unit, we're going to be covering that probably in about a month and a half, 2 months. The way that we would test an alternator is with this, but the thing is you have to get the alternator to put out its maximum, and on a modern car, it's computer controlled. So on a modern car, you'd actually go in with the scan tool and you'd go to the alternator and do like a field test or like a full field alternator, command it with the computer. The computer will ramp up to 100% duty cycle, and then the alternator will be like, all right, I'll give you everything I got, and we can measure it like this, like, oh yeah, alternator is doing 100 amps, that's good. But if the alternator is only making 60 amps, and it should be making 100, then we would know that the alternator's either A, got, an external problem that's not giving the right signal, or B, the alternator itself's defective. And so there's a little bit more to that than you're ready for, but this is a good tool. Thought it'd be good to explain it while we talked about the effects right here. And so the other thing is, we did a very small couple experiments out there. If you had the 194 bulb, the little bulb, it pulled about 1/4 of an amp through the system. Who substituted a bigger bulb with more light? What happened?
More app.
More amps. All right, so I agree. You measured that, you verified it. Did it make sense why there was more amps going through? It's a bigger light, it's more light, it's more energy, right? It kind of makes sense. But now let's make sure you understand that with Ohm's law though. Because remember, Ohm's law is not something we use for a customer car, but it's something you have to understand the relationship. If you have a 12 volt source, remember this thing that we drew a little bit earlier? Oof, I'm striking out on the markers. This black one I know is good. VAR, your 12 volt source is here. Let's say, I actually don't know what the resistance of that 194 bulb is. So first let's calculate that. If we ended up with a 0.250, right, or a 0.25, it's the same number, could we determine the resistance of that bulb? The answer is yes. How? Cover the R. What are you left with? 12 over 0.250. So 12 divided by 0.250. Can anybody run that number? I'll do it on the calculator just so we're all clear.
48.
So we can just, to make the lesson really relevant, it's 12 divided by a 0.25. You can add the 0 if you want. So you're looking at what? 48. So if we just get that number 48, what's that mean? That means that 194 bulb resistance was 48 ohms. But if you were to measure it, actually, if you were to just pull the bulb off and measure the bulb, you probably wouldn't get that number. And that's because when you're using your meter, it's not hot. It's just cold. And normally, when materials get hotter, they get more resistance. So actually, a really good way to test dynamic actual resistance with the filament hot is to do the volts and the amps, and then you can calculate the actual resistance with it hot. Kind of weird, think about it. So Ohm's law does work. Now we put a bigger bulb in there, and let's just say that bigger bulb only had, we'll get rid of the amps. That bigger bulb, let's put a bulb in there with 6 ohms, okay? I just did math in my head. You're gonna be impressed. If I have one with 6 ohms, anybody think they can determine the amps?
2.
Exactly, boom. 12 divided by 6, 2 amps. Who got 2 amps with the bigger bulb?
I got 1.9.
Oh, come on, give it to me, 2 amps. You tell me 1.9. Nah, just kidding. If you got 1.9, that means the amp's just a little bit more than 6. But see, so when you have the circuit that has less resistance, there's going to be more amps. You proved it by putting the bigger bulb in there. You went from a 48 ohm bulb to a 6 ohm bulb, and your amps went from 0.250, a quarter, to 1.9 amps. So right, so you're proving these Ohm's laws. So that's part of what we're trying to do, is just make sure you understand the relationship. And then you'll see as we get into this a little bit later, my break point was actually going to be in about 5 more slides last week, but we were thorough on the voltage. So we're going to have a little bit of a break point, and then we'll tie in why it's so critical to understand all these, because right now it's just concepts. Cool. You've only done a few basic measurements and you're like, more theory? Yes, but you'll see why. Now we'll kill the calculator. We're kind of good on how to measure amperage, right? Good on the effects. There's your current clamp. And then, like I was saying, here's it actually measuring the battery. So I thought I didn't put this in there, but now I remember I did put this in there. So that was, it's almost thinking like I was thinking a week ago or 2 weeks ago when I made this. The next one And the final basic measurement is going to be measuring resistance. So when we talk about measuring resistance, you already got a preview because we had all those blown fuses. So we couldn't measure amps because the fuses were blown. So if you want to measure resistance of a fuse, you guys know we could take this meter. We can move the lead back to the V, the ohm, like all those symbols, right? And then we're actually just going to put it on ohms. And then just like what we show here, if you want to measure resistor, you just do this, boom. And you're measuring the resistance. If you wanted to measure a dimmer, like the dimmer is sometimes the little knob, like let's say you have instrument panel lights, you can make them dim or bright. You could actually check the dimmer like this. You could check the switch like this. You could check the fuse. You could check all these things by measuring resistance. So it's a very valuable one. Mason, you had a question? I saw your hand.
How do you do that on the circuit board?
I'm going to show you. In fact, technically you could do it without the circuit board, but just to make sure you understand, remember we had the red one here. No, get it back over to here. Okay, it's back. Volts, ohms, diode test. We need to move the lead. Otherwise you won't get a number. It's not that you'll kill the meter, but you won't get a good number. And so if you look at measuring resistance, there's a couple things you must notice. When we measured this resistor, where's the resistor? It's out of the circuit. Make sense? When we measure this dimmer, what did we do? We disconnected it. You can't be measuring resistance with any sort of power flowing through the system. Make sense? There can be no current flow. So that's not to say, technically, you could leave it connected, but I want to make sure that you understand, if you leave it connected and you try to measure it, right? You see, I'm trying to measure the dimmer, but your meter is going to use its little, I was going to say a 9-volt battery, but we just had these power probe meters apart. And what batteries were in there? You saw them.
600.
No, not the fuses, the batteries. Okay, were they triple or doubles?
Triple.
All right, I believe you. I didn't look that closely. So it's going to use the 3 AAAs. The purpose of those 3 AAAs is to run this little screen and stuff, but also it's going to take those AAA voltage, which I think might be like 1.5 volts each or 1 volt a piece, and it's going to basically, using its batteries, send its own electrons out, send them through something, and then measure how difficult it was for them to make it back. Make sense? So if it's using the little AAAs, do you see how that would be a problem if the big battery was actually still sending power through here? It would mess your measurement all up. So you have to have it powered down. You have to. It's best to have it full on disconnected, and here's why. If you leave it connected, which sometimes I do, okay, I won't lie to you, sometimes I do. Because sometimes it's actually hard to disconnect it. But if I go ahead and I go to measure it, and it's still connected, yes, I'm trying to measure through the dimmer, but I'm also sending out electrons to wherever they'll go. So sometimes you're seeing the simple circuit when in reality, maybe this fuse goes back to the fuse box and there's a whole bunch of fuses there, and there's a secondary connection to where it could make it to the lamp. For example, if this lamp was the headlight, but it also had daytime running lights that use the headlight, this could actually backfeed to the fuse, to the DRL fuse, and then find its own janky way through the body control module and stuff. So you won't get a really true accurate measurement unless you disconnect it completely. But if I go ahead and I go to measure something such as the lamp, and I know the lamp should be about 6 ohms, and let's just say I get OL, what's that tell me about the lamp?
No good.
Yeah, it's open. It's out of limits. Remember, because this can measure up to millions of ohms. But if it's got more than millions of ohms, it just says OL. So essentially, remember, OL means kind of like open circuit. Now, if I get a measurement of 792 mega ohms, what's that tell me? Is that? Ooh, and that's why it gets a little weird. So 792 mega ohms is not technically an open, but it's way, as you may say, hella too much. That's hella resistance. Now we're picking it up. So you know what? That thing is still cooked. It's still cooked, but the reason I'm not getting OL might be because the electrons are going through the other fuse and a different fuse and the module and the whatever and the whatever and whatever. But the thing is, for my practical application, I'm looking for this lamp to be 6 ohms. If it's 792 million bajillion hella cooked, that's still cooked.
Yeah.
Okay, yeah. So I don't really exactly care. Sometimes I'll just be down and dirty quick, not even disconnect the lamp and just, because here's the practical problem. You want to measure the lamp, right? But a lot of the times on the car, the way we're doing this is back probing. If you disconnect the connector, you push it to the side like you're supposed to, now you can't back probe that part. Makes sense? So now you're like shaky hand, you're like trying to touch the terminals and you know what I'm saying? Whereas like if I leave the connector in there, I can make a nice clean back probe using the little T-pins, okay? So that's like, I'm defending myself why I don't always follow the rules, you see? So that's how you can do it. Mason, your question was how do we do it on the board? The best way to do it, you don't even have to be on the board. You can literally take the component and you could come in here and you could sit at your desk and you could measure it. But the way that we're going to do it is we're going to do it on the board. You're going to disconnect both sides of it and you're going to measure it. And you're going to measure fuse, switch, dimmer, you're going to measure individual components. Because remember, when the customer comes in, they're not looking for us to do calculations. They're like, hey, my bulb, this lamp doesn't work. And then you're like, all right, we were just talking about AutoZone, right? If you're working at the AutoZone and they say, hey, my headlight doesn't work, and you're there at the counter, what are you selling them?
Light bulbs.
Probably, and then if you put the light bulb in and it doesn't fix it, then what?
So
Fuse.
You could be making a lot of guesses, right? But typically, the non-professional runs out of juice right there. They're done. The bulb doesn't work. I put a new bulb in. It doesn't work. And now they're like, let me bring it to the mechanic. And then the mechanic is like, well, it could be the fuse. It could be the switch. It could be the dimmer. It could even be a brand new bulb that's no good. Ronnie had his meter that's brand new and that the fuse is no good inside. I mean, there is defective brand new stuff, right? So to go about it in a way where it's like, I'm going to replace the most likely things until I happen to hit it is like, that's not, you want to be a sniper. If you want to be good at this, you want to be a sniper. You want to be like, boom, one shot, kill shot. Fuse is no good. I measured it. I proved the fuse is no good. I replaced the fuse. Pay me. Make sense? That's our goal. Sometimes it's difficult to do that. I'll give you that. Once in a while, I'll weigh out how much time it's going to take me to pinpoint diagnose it, and I may be like, you know what? I've seen so many times where these dimmers are no good. Like, it's kind of hard to get behind the dash and take these measurements and measure the resistance of the dimmer. I've done 100 dimmers, and that's the only thing that's ever been wrong. I may guess on that one. But what I'm trying to train you is to perform the measurements and do the kill shot every time. So for now, let's go through how we could do that. Like same, and by the way, same rules apply. If you get a measurement, in fact, let me switch the order and we'll come right back to that. If you look at this, and we'll talk about the measurements, and then we'll come back to some of the things that go wrong, because I think that'll make more sense once you've covered it. If we go to measure, let's say, the fuse, how do you think we would proceed with that? Because I just proved to you, these fuses can be no good, and they're not clear, and you can't see, okay? So if all you do is you pull fuses and you look at them, you ain't the real mechanic. You're working the parts counter type of mechanic. Make sense? So how could we measure this fuse? Picking up what I'm putting down. We're on resistance now.
We would just have a point from before and after.
Yeah. So I move the lead back to the V, ohms, whatever. Put it on resistance. In fact, I'll use the meter first. And then this is how simple it is. I disconnect, and I measure just the fuse on resistance. Make sense? So if I showed you that, and now I become the meter, what type of reading should I get?
0.2?
Yeah, 0.2, 0.1, 0.0, that would all be good. What should I definitely not get? OL, if I have an OL, what wrong?
The fuse is bust.
Fuse is what wrong? The fuse is no good. Boom. If you can see it, you already knew that. If you can't see it, now you just measured it, that's a little bit better, okay? But let's just say I measure the fuse and the fuse tests okay, but the bulb still doesn't work. What else could I test?
That switch.
I could test the switch too, yeah. And this, if the switch is closed, should measure more or less like no resistance, 0.2, 0.1, something. What about if I were to measure here to here? What's that measuring?
The wire.
Exactly. You can measure components, you can measure harnesses, you can measure wires, you can measure connectors. Resistance is a great tool, a great measurement. Some would call it continuity. If the wire has continuity, it's going to have low resistance, right? You could even put it on the continuity test and it would go beep, beep, right? You can even help make it audible if you want. But some I explained the last time though. This is the negative. I'm going to show you the negative right here. Let's say we just tested that wire and the resistance tested okay. In fact, let's even make it the fuse because that was the example I got last week. That was an amazing example. That fuse is worth so much more money to me than a good fuse because that fuse failed in just a way where I could prove my point. On that fuse last week, if I disconnected this and I measured it, I would get this number. Or so. Cool? Is that fuse good or bad? So you thought, so I would have thought, and that's why when I saw it, I was like, whoa, that's crazy. This is the thing. If that fuse is like, we'll draw it a little bit more accurately. You know, that fuse is about like this thick right here. It's about that thick. What if that fuse, right, you could flow 10 amps through there, but what if that fuse is like kind of messed up and it's almost like a pipe, cool? It's almost like a pipe and there's just this tiniest little passage. When you put it on resistance, you're using the little AAAs or the 9-volt battery or whatever, and it's just sending a very small amount of electrons. That very small amount of electrons breezes right through that little mostly clogged up pipe, cool? And so it's like 0.2 ohms, we're good. You think it's good? That fuse was bad. This wire can happen all the time. That wire, if you look at a cross section, it actually looks like this. There's tons of strands in there, right? What if all those strands were corroded or broken or whatever, and there was only just one tiny little strand left? Putting on resistance will pass this. Putting on resistance will pass this. What would find out that they're actually a fail, not a resistance measurement?
Actual voltage going through.
Bingo. So when you test it active, when it's live, when it's like trying to run actually closer to 10 amps through there, what you do is you do a voltage drop. You might get 12 volts going in, but you might actually get like 1 volt coming out, and you'd be like, oh yeah, that thing is like a clogged pipe. Cool. A lot of water tries to go in and just a little trickle comes out. So resistance measurements, very valuable, very valuable. But a voltage measurement is actually a lot more accurate. Makes sense? A voltage measurement really tests the circuit running. The health example I always give, anybody in here think they're in pretty good shape? You think your heart's really strong? Well, I'll test that theory. Take you, put you on a treadmill, tell you to run as fast as you can, as hard as you can for 10 minutes, and then retest it. Then we'll find out who's actually in good shape or not. You see what I'm saying? So like, I want you to do an active test. You know they call that the stress test. Yeah, it is. The stress tests, they're big time.
2 of them.
Well, that's because they know they could put you on the little blood pressure thing and they'll be like, oh, you got blood pressure and stuff, you're good to go. But that's like testing resistance. Make sense? You want to really know what you got? Put some stress on there, put it under some form of load and be like, yeah, well, now we'll really test it. Kind of similar with what we do with transmissions. If you just drive a car nice and light, it might not slip. But if it's starting to slip, like worn clutches or seals that are leaking, if you try to put it under wide open throttle, it might start to slip under wide open, you know. So we want to test it in the most thorough way when we're trying to find these problems. Cool, so that one would be a good little tip. Like I worked next to a tech back when I was in New York, so we had a lot more corrosion. So admittedly, where I was at, we had a lot of this type of crap, but I remember he had an ABS problem, and the ABS module was not, I think it was just full on no communication with it, and he like tested the wire from point A to point B in resistance, and it tested okay. And so he diagnosed it as the ABS unit, and he put a new one in, it didn't fix it. And then he ended up having to get the foreman, and the foreman's like, how'd you test that? And he was like, I tested the wire. And he said, let's turn the key on and see what voltage is available at the module. And it was like 4 volts. And he's like, this module can't run on 4 volts. He's like, but I tested the wire. I tested it with resistance. And this is part of the reason I know some of these things is when somebody's making some mistakes, you know what I'd be trying to do? Listen so I don't make them. And then I put it on social media. No, like that's not really what I do. I just listen really carefully because I'm like, I already done the School of Hard Knocks. I don't want to do no more School of Hard Knocks if I can help it. So I'm always trying to learn from any situation that I can. Cool. So we're gonna pause, and you guys are gonna go do some resistance measurements following this. So get a picture of this one. You're gonna measure resistance from A to B, B to C, C to D, etc. Tim, if you pause me, we're rolling. Okay, ready? We're back. Before we get ahead of each other, let's remember we got the same issues when we measure ohms as like when we measure volts, millivolts, and etc. We're rolling. Okay, so this is a problem that'll burn you on every measurement. Volts, ohms, and resistance. Volts, amps, and ohms, all that stuff will get you messed up. So let's say if you're measuring a wire and you get 0.2 ohms, is that good or bad?
Good.
That'd be good. Yeah, exactly. What if you get 200, what if you get 0.2 kiloohms?
That's bad.
Okay, see how this is so important for you to understand. 0.2 ohms is good, 0.2 kiloohms would be really bad. Here's the difference. 0.2 ohms pass. If it was 0.2 kiloohms, what's that mean in ohms? Kilo is 3, so that would be 1, 2, 3. That's 200 ohms. 200 ohms on a wire, now that you guys just did the measurements, right? 200 ohms on a wire would be no good. So let's do a couple math things and then we'll summarize what you got. So here we have 2,458 ohms. How many kiloohms is that? Kiloohms is here. If we're going to go to ohms, you got to do a 1, a 2, and a 3. So what you get?
So it'd be
0.0255.
Okay. I actually explained that backwards. Because we're going from ohms to kiloohms, ohms is here. We're going to go 3 to the left, might be. So we were here, right? 1, 2, 3. 2 kiloohms, 400.458. So that's like almost 2.5 kiloohms. Cool. How about 0.896 kiloohms to ohms? Kiloohms would be here, ohms would be here, so we'd be going to the right. Wouldn't you say? 1, 2, 3 is 896 ohms. Okay, good. So you guys understand the relationships there. That was good. But let's go. In fact, I'm going to keep this up and let's break down the circuit that we just did. And just actually, let's do one more because I forgot. Sometimes you'll get actually mega ohms. I saw some mega ohms readings out there. So kiloohms is thousands. Mega is
million.
Bingo. So if you had a spec that was 1 to 2 kiloohms and it popped up on screen real quick with a 1.5, you'd be like, oh, it's good. But if it was a 1.5 mega ohms, that would be like way out, really bad. Okay, so let's do a 5.87 milliohms to ohms. You'll notice this is very different.
Sure.
So look at million ohms is how many digits?
6.
6. Okay, so it's a similar process, but a much different number. Ready? 1, 2, 3. That'd be a 0. And then we do 1, 2, 3 more, and that'd be a 0. And that gets kind of sloppy, so we'll do it up here, okay? 5, gonna stick with the black marker, which I had, and I did something with.
Right there.
There it is. Set it right there. Let's do a 5.87. By the way, when you leave the meter on, it starts beeping because you're draining the battery. So if you hear that beep, it just means you left it on. Just turn it off. Okay. So we're going to do a 1, a 2, a 3, right? So now you're here, and 3 more. So our number is 5, 8, 7, 0, 0, 0, 0. So what the heck number is that?
5,800,000.
Exactly. It's over 5 million. Make sense? So if you get a reading on your meter of 5.87, that you gotta for sure know if there's a K or an M right there. Make sense? Okay. And then how about this? We have 3,234,000 ohms. How many milliohms is that? Decimals here, right? This one's cleaner. 1, 2, 3. Oh, that was my meter. Wasn't it? Okay, yeah, that was the meter that I had for the day. I'm fired. You can fire me. 3, and then 3 more would make it
3.234.
Do you see, though, why the meter will auto-range? It doesn't have enough digits to show all these, and that's why it'll automatically bump over to K or to M. Now, I'm gonna give you a bonus lesson because I think it's relevant, but it's a little bit different.
Paul, are those numbers practical? Are you going to see those specific numbers that you're showing right there?
You can, yes. So with daily types of things, mostly we're seeing ohms. Like with wires, ohms. With bulbs, generally ohms. With LEDs, though, kiloohms. With some very, very small current electronics, mega ohms is a thing, yes. If you're measuring a wire, though, you should automatically be thinking, like, you should be predicting, I should have like a 0.2 ohms, a 0.1 ohm, like a 0.0 would be good. But yeah, these are real things. Like if right now we wanted, I want to pick a subject that's unrelated to electrical, a little bit more applied. I'm thinking engine performance. If we were to check a, let's say variable valve timing solenoid, they could give us a resistance. It will most likely be in kiloohms. Mega ohms, not so much, but kiloohms, we would definitely get that. If they were to tell you to measure a particular circuit in the ECU, that would probably be mega ohms. That would be like a very uncommon measurement for us to have to do, but you'd have to do it, yes. Okay, how about, we talked about the big numbers, right? What about, you remember I drew you this thing? It was this. Kids have dropped over dead converting metrics, right? And here was kilo. And then if you went 3 more, I don't even remember what these are, you'd be mega over here. Do you guys remember there was something over here and it wasn't a big M, actually it was a small m? Do you remember what that one is? Milli, yeah, exactly. You can measure milliohms, but this is something that I was always kind of like, we always talk about kiloohms and mega ohms, but we never really talk about milliohms. Well, I'll tell you, plain and simple, this meter doesn't have the ability to measure milliohms effectively. Like sometimes they even have a setting for it, but it's not very accurate. The reason I like to include this is, I heard beeping, but I think it's off, is if you were to get into the hybrid EV stuff and you had, you creep. I'm gonna take that and you had
For DC, it's million.
yeah, I'll even write it out. So this would be a centi right here, and this would be milli, right? Like millimeter.
Yeah.
Cool. 10 millimeter is a 1 centimeter. Makes sense. So with milliohms, your meter is not precise enough to measure that. So if you get into a hybrid EV and you need to measure the 3-phase motor, remember there's 3 phases, U, V, and W. If you wanted to measure U to V you would probably use a milliohm meter, and you literally, it's so simple. It's just like what you all just did. You just literally isolate it from the circuit, put it on resistance, and you measure from this point to this point, and you get a number. But these meters can't measure that precisely, so you get a specific tool that's called a milliohm meter, and then you can measure down to the milliohm. So if you were to talk about this number, I mean, this is going to be a crazy number to show you, but if we had 5.87 mega ohms, right? So this is our number now, 5 million, oh, black, not blue, 5,870,000. Okay, you want to make that into milli, you know what you need to do? Add 3 more, right? Because it's here, we need to do 3 more decimals. So what number is that? Is that a trillion or a billion?
Yeah, that's brilliant.
That's so much, I don't even know for sure. But you see, like, your meter, if your meter can measure, it can't measure really that detail. That's how small a milliohm is. A milliohm would be like, oh, you want a milliohm? Here, I'll give you one. If your bank account looks like this, let's talk later. But if I give you this, like, that made no measurable difference at all to your bank account. That thing is that is like, all right, if this is more realistic, this is where mine stopped right there. You didn't give me a 1/10 of a penny, 100th of a penny. You gave me this thing. I have to get like a million of these before I even get $1. Okay, so this is like nothing. This is like so tiny to just show that on a scale. And that's why our meters just aren't, they're just not made for that. They're not made to be that precise. So when you get into milliohms, no. Now our meters can measure millivolts and milliamps. Yes, they're made for that. But milliohms, no. They don't do that. Special meter for that. Okay, now that being said, let's go back to kind of where we were. You guys did these measurements. They should have been pretty simple. This is just summarizing how these auto ranging could throw you off. So if you were hoping for 10 ohms, and you look real quick, isn't this good? No. That's 10,000 ohms, and this is 10 million ohms. This is basically an open circuit. This is a lot of resistance. This is in spec. This is like maybe pass, fail, but in one way, and fail, but like as open, right? So you don't overlook that. Don't look too quick. Make sure you look for that little K or the mega. And then we got to this point, and let's discuss why this is so practical, and then we're going to actually do it together. So let's say this is a customer's vehicle, and what bulb do you want this to be? You get to pick some bulb. What bulb? But like, what's the bulb do?
Turn signal.
Turn signal will be a little tricky because that has to flash. Brake light, I like brake light. Brake light, cool. Here's your fuse box. We got a fuse in there for the brake light. It goes through a switch. Think about this. When do your brake lights come on? Okay, so this is the switch that when you step on the brake pedal, it closes it, exactly, boom. So now we're on the same page. And then this is the harness, and then this is your brake light bulb, and then this is your harness that goes to ground, okay? Customer comes in with an inoperative brake light. First off, it's a little bit misleading because do they have one brake light? They have multiple, okay? And that's actually the next thing we go into is how we diagnose a series circuit different from a parallel circuit. So in a parallel circuit, you actually have more than one bulb. So if one bulb is out in a parallel circuit, you could do like a much quicker diagnosis. But let's just say it's a series circuit and they only have one brake light because it's a motorcycle. All right, this customer got themselves a motorcycle. It'd be a good idea, huh, Mason? Yeah, it would. All right, if that's the case, let's discuss. I need to stop setting my stuff where I can't keep track of it. If I'm the meter, and let's say you go to the Vato Zone, and Vato Zone says, "Yeah, put a brake light bulb in there." Bam! You put the brake light bulb in, it doesn't fix it. Then what? take you to the mechanic. Now you, the mechanic, how do you want to proceed with this diagnosis if the only thing you could do in this exercise is check resistance? What do you want to check?
Check the origin first.
Pick whatever you want, I don't know. You could check the bulb, absolutely. Disconnect.
You gotta test the connectors, don't you?
You can, but for now we'll check components to start. So if we disconnect and disconnect, we're checking literally just the bulb. And what do you think it might have approximately?
0.24.
Probably 0.2 is too low. 0.4 is kind of low. It's the load. The load of the circuit should have 6 ohms, 4 ohms, 2 ohms, 40 ohms, 80 ohms, I don't know, something like that. Remember we did the math before with how many amps? We had one that was 48 ohms, right? So that's a pretty high resistance little tiny bulb. So yeah, we should have some resistance here. What if the bulb is blown? What would we get? OL, so out of limits. Why is it out of limits though? Yeah, because remember, your meter can measure up to millions of ohms. If you have a filament and there's a break in it, that's going to have more than millions of ohms. That's an OL. It's out of limit. Now, yes, one of the textbook calls it overload, but it's not overloaded, so that's why I get so like stressing out, not really, but it's just out of limits. It's just so much resistance. That would be a bad bulb. But if we measure it and we get, let's say, 6 ohms, what's that tell us?
It's good.
All right, I'm going to do this before I write on this canvas thing. I've done that before. Not today. Be a little too excited. Okay, so if this is 6 ohms, that's good, right? Check. That's good. Are we selling the customer another bulb?
No.
Did they waste money on a part they didn't need? No. So you see why our measurements are worth money, because we're saving the customer money by not guessing. All right, what else do you want to measure?
Yes.
Okay. What should I get on the fuse? Yeah, 0.000, 0.001, 0.2, 0.2, like any of those is decent. We shouldn't get something like 6 ohms. This one we said was 6 ohms. Okay, this one, let's go with a 0.2. It seems to be the most common that I see. That fuse is good or bad?
Good.
Fuse is good. I love it. Like it, love it. What else can we measure? Okay. And if I were to put it on the switch as it's drawn right now, what should I get? OL is correct because it's open, right? It's over the limit of millions of ohms. There's a big air gap right there. Cool? Now when I step on the brake pedal, what should I get?
0.2.
I should, but it might be kind of common to get maybe potentially the max, by the way, would be a 0.5 ohms. That's like on the high end, but that's still a pass. Cool. So this one is check, good. This one just check, good. Wait a minute, all the components are good in the system?
Wires.
Oh, the wires. You see, so if you have an electrical problem, you could sell every component in the circuit, but it could be the wires too. The wires are a component themselves, right? So how could we check this wire?
You unplug it and
So we disconnect it and we measure like this. What do you expect?
0.2.
So that's good. And how about this?
0.2. 0. Yeah. 0.2.
That's what I got.
It's open.
That's what I got. No, it should be 0.2, but this is what I got. What's wrong with the circuit?
It's the wire.
It's the wire. So what am I selling the customer?
Wire.
All right, good point for a lesson. When you say a new wire, you can't just like roll down to the store and be like, hi, I'm working on a 2020 Honda Accord. I need a new wire. And they're like, huh? Like you can buy wire. You can buy bulk wire. You can go to the Yonke yard and you could start cutting wire. If you don't want to repair the wire, you need to buy the whole wiring harness. That sucker's got bunches of wires. Like remember we were talking about that inductive amp clamp? If you want to measure the circuit, you would need to pull that one little wire out and measure just the one wire. You don't get to put this on the whole big old pack. You can't measure everything expecting to measure one. Make sense? So that conduit, which is like a wire harness or a loom, could be like a big old fat piece. If you want to replace all that, you could do it. But a lot of those wiring harnesses new, $2,500, $3,000, $4,000, a lot of money. So maybe one of the next things that we cover was that chapter 11 that we had a chat about earlier. Yeah, wire repair, how to repair the wires, how to do like all that. I want to teach you all that stuff because if it's this wire right here, I'm going to repair that wire.
Or
Uh-huh.
to see where the wire's going to.
Yes, and so you got to get down nitty gritty. All right, so when we think it's this wire, remember we tested between the switch and between the bulb itself. So that could be 1 inch or that could be 10 feet. So if that's the best that you can do, then you know like, oh, okay, it's in this big length of wire. You might, at that point, you got a couple options. Some are good options and some are bad options. One, you could start stabbing this insulation, stab it, right? That's kind of bootleg. That's not really nice. That's like you go to get your nails done, remember, and they bust out like the hedge trimmer, like, whoa, chill. Like, I'm not trying to have more damage done. I just want my nails done. They just want their light to work. They don't want you stabbing up a whole bunch of stuff. So sometimes what we're doing, we're probing here. If you know it's between point A and B, the next step might be to actually start to access the harness and look for damage. Typically a wire in the middle of the harness doesn't just break. You know, it'd be like, let me see, is there some damage? Is there something where I see some evidence of rodents, right? You've seen some evidence of rodents. You know, you start getting clues. Then a lot of times if you can measure from here to here and know it's the problem, you know it's the wire, but you may spend an hour or two getting into it further. Like I told you, that one car in one of the earlier times we talked, I had to pull the front bumper off of it to inspect the wire, and I ended up spending several hours on that diagnosis. But if you give me a good diagnosis and you can fix one wire, that's a good job. Like I'm good with that. It's probably not going to be that cheap, but that several $1,000 harness plus hundreds of dollars of labor is it's not cheap. Once it's to that point, it's not going to be cheap. And then as we get further into wire repair, I think you'll understand more. But just for the diagnosis, we can do the diagnosis just like that. Now there's one more thing we're not exactly factoring, and without getting too much into health class, you know, at each one of these, there's a connector, right? So you guys know on the board, you know, it's much more simple. Like we use these BNC, like banana connectors or whatever. This is the male, and then this is the female, and there should be some tension there. You notice they fit well. It's like you gotta push a bit. That's gonna probably be a good connector. But if you try to push the male into the female and it's just kind of like this, that would be like, wait a minute. So everywhere in here, you have a potential bad connection from male to female, 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 male to female. So every connector is a potential point of failure. And I've had literal cars bought back, you know what that means, lemon lawed, right? That have had 2, 3, 4 attempts, and then the customer's like, you know what, this car's a lemon. Get into them a little bit further, we could do like either a voltage drop would be better, or if we just focus on resistance, I could actually measure the resistance from the male to the female, and I could get a bad number. That male to female connection should be definitely 0.2 or less, like preferably less. And if you got a 0.2 measurement and then you did a little bit of wiggling and all of a sudden you got an OL and then you got a 0.2 and you got an OL, it could literally just be the terminals. Sometimes we pull them apart and the male terminal's bent, the female terminal's opened up. Sometimes water has gotten into the connector and they're both corroded, one's corroded, you know, like, so I like the focus of the activity is measure the components, but I want you to know, remember, there's connections here that are like, they need to be clean, they need to be tensioned. The DIY people who don't really have the training, they're like, oh, disconnect those and like put dielectric grease in there and plug them back in. That's a cool maintenance, but if the terminal's opened up, the grease doesn't fix anything. If anything, it might even make it a little bit worse. And so, you know, each point has the potential for a failure, and all this is just for one brake light on a motorcycle. So you can see now some of the diagnosis can get pretty thick and pretty complicated, but this is what really, you know, this is a top tier, top dollar. Remember I told you about a student who only graduated with me like five years ago maybe? I remember he graduated with a mask, so that was during COVID. Like he's $42 an hour and making like a whole lot of hours per pay period and getting a pay differential for being a team leader. Like this is somebody who really got this. This is somebody who, when that car is about to be bought back, he's like, no, let's be thorough and let's check the male-female terminals. And they find one tiny female terminal that's a problem that you could fix for $1 that saves that car from being bought back. He's pretty good at writing, though. A saying, the pen is mightier than the sword. He'll write all of his diagnostic steps and all the steps he did, and they'll pay him a whole bunch of time for diagnosis, though. But the actual repair was very small, but finding out where the repair needed to be was more of the work. Kind of make sense? So hopefully that made a lot of sense to you. Now, we'll go through a couple practice exercises to make sure you definitely understand what we needed to do. And then we'll talk about the effects. And then we're going to measure one on this board. And then we'll really make sure you understand what some of the more typical problems in the car would be. All right, so this is designed to help you understand how to use the meter, but also, and how to measure resistance, but also like what the effect of the resistance is, okay? So let's just say we're checking components, right? Components or circuits against what? How do you know what's good or bad? A wire, for example, you don't really need this spec because a wire is a wire. Cool. But what if you're checking a bulb or that VVTI solenoid I talked about or a sensor or something? How do you know what it should be? Exactly. So if let's say that you're testing a coolant temperature sensor. If you want to test a coolant temperature sensor, we test those on resistance. We do it all the time. You all can test resistance now. What's a good measurement? What's a bad measurement? I don't know. Got to look it up. Got to look it up on manufacturer specifications. So if you got into auto, because this is something I hear other teachers and other departments say a lot. Yeah, they want to work with their hands. They don't really want to study. They just want to get their hands dirty. Okay, cool. The dirt's outside. You want to dig and play in the dirt, roll in the dirt, whatever. But if you're trying to actually diagnose the car, a lot of your work is like this. Let me go look up what is the spec. What is it supposed to be? Then you get your meter and then you measure it and then you determine, is it in spec or is it out of spec? So I'll give you a range. The coolant temperature sensor at 68 degrees. What do you feel like the temperature is in here? You nailed it? 65?
62.
All right. 62 degrees should be 1 kiloohm. Cool. I look it up in the manual. At 62, 1 kiloohm. You know what that means? 1,000 ohms. If I put my meter in there and I get 1,007 ohms, what do you think? That sounds pretty good. Yeah, I mean, it doesn't have to be perfect. If I put my meter on there and I get 7 mega ohms, what do you think? Yeah, that sensor would be bad. That's a big part of what we do. We look at a spec, we perform the measurement, it's in spec or it's out of spec. Make sense? But if you were to ask me, like you guys ask me some really good questions sometimes, and you're like, hey, I'm measuring this coolant temperature sensor and I'm getting 12.7 kiloohms. Is that good or bad? I'm going to say, you know what I'm going to say? I don't freaking know. I have no idea. However, we could look it up, and that's what we do. Some things you memorize. A wire, the wires are all the same. Sensors, I don't expect you to generally memorize a sensor. It's just not likely, right? So that's what we're doing. Look up the spec, measure the component. It's in spec or it's out of spec. If it's in spec, what should we do? Look for some other problem, right? And that's kind of the point here. If we have a specification and it passes, don't replace that part. We're going to check another part. And if that one passes, we're going to check another part. And hopefully you find a part that's out of spec, right? And then you replace that part. That's how you hit the target. That's how you get the kill shot. That's how you get like, I measured this, it was out of spec, I replaced it, I fixed it, boom. Make sense? That's what we're shooting for. And then another thing to remember, the current flow is inversely proportional to resistance. What the heck's that mean? Inversely. That means when one goes up, the other goes down. So if my resistance goes up, what happens to my current flow? It goes down, exactly. So when we start to see problems in the circuit, like high resistance on a ground, high resistance in a wire. What's going to happen to the brightness of the bulb? It's going to be dim because the amps go down, right? The current flow goes down. So when you walk up to a circuit, you kind of want to interpret it a little bit. Like, oh, the light bulb works, but it's dim. Right off the bat, I know there's unwanted resistance somewhere. And last week, we talked about voltage and voltage drop. If there's unwanted resistance that's excessive, it's going to drop excessive volts right there. Remember, so if we have $12 being passed down, and the one and only bulb's expecting 12 bucks, and it only gets 6, it's not going to glow real bright. Where'd the other 6 drop? You can measure that as a voltage drop, or you can measure individual components with resistance, and you'll find something that has high resistance, and then you know you nailed it. Make sense? 2 different measurements, both checking for the same type of thing. Just make sure you know my go-to is going to be the voltage drop because it's active. It's the stress test. Okay? So that's kind of what this is saying. Higher resistance, less current flow. Lower resistance, higher current flow. So if a fuse is blowing, it's not blowing because excessive resistance. It's blowing because not enough resistance. Low resistance causes high current. High current blows fuses. Make sense? Kind of 2 totally different things we're looking for. If the fuse is blowing, I'm looking for shorts. If the light is dim, I'm not looking for shorts. Do not tell me the bulb was dim, I found a short. Because if I read that, I'm thinking like, you're either lying or you don't know. Both of those are a problem. All right? Now, you're okay to make those mistakes right now. But I'm going to help you correct those. Dim bulb, high resistance, blown fuse, short. Typically, that's what you're looking at. I had a service advisor who I'd write these really extensive, very technically accurate stories on how I diagnosed it. And he was always kind of like trying to shorten them so he didn't have to type as much. This was back in the day when we would write our story by hand on the repair order, and then the service advisors would type it in the computer. Those days are gone. You're going to type your own diagnostic stories yourself, okay? So that's better. But he would constantly just reword my stuff. And then one day I was looking at what he typed, and I was like, you said a short. He's like, yeah, it was an electrical short. I'm like, no, it wasn't. It was open. He's like, well, whatever. I'm like, no, dude, seriously. This is something that has to hold up in court, potentially. You know, this is getting submitted to the manufacturer because it was a warranty claim. So it's like, no. An open is high resistance. It's OL. A short is low resistance. They're so different. And it was like very frustrating. So you guys have to know the difference. Cool? Explained right there. Now let's go with this one. All right, if we were to look at this one, and you know, if you wanted, you could measure amps right here. You could measure the resistance right here, or you could measure the voltage right here. You could measure resistance right here. You have to understand how they all work together. So first things first, if you want to measure resistance, how would you measure resistance of this thing, this resistor?
After the amp and after resistance.
All right, so you already measured it out there. If this was a bulb, don't make me draw on it. You disconnect it, right, and you measure resistance like this, you get your number. Cool? If you wanted to measure the voltage of that thing, you'd actually have to have it plugged in and have it turned on, and then you could measure the voltage drop like this. See how they're different? But I'm going to tell you why they're in a way a redundant measurement. If your resistance is supposed to be 6 ohms, but it's 12, what's that going to cause for amps?
Drop.
True. By how much? It was supposed to be 12. I mean, it was supposed to be 6, but it's 12. So isn't it double? So if we double the resistance, what's going to happen to the amps? It's proportional.
It'll cut in half.
Exactly. Boom. So double the resistance is going to make half the amps. That's going to make the bulb dim. Cool? If you were to look at it like the voltage drop, let's say that the resistance was actually increased over here. If you were to have the resistance of the circuit double, let's say you had, I'm going to actually have to draw a little bit. And we're going to describe this problem a few different ways, okay, just so you can know these are all going to be tools in your tool belt. So the spec for this the spec, I'm going to draw it like this. The spec is 6 ohms. And you measured the resistance, and the actual resistance measurement, do you remember what it was? You measured resistance, though, from, let's say, like here to here. The resistance was 12 ohms. Okay? But then let's just say you got further down, and this was actually 6. So if this thing itself was actually 6, but here to here was 12, doesn't that mean there's like 6 ohms somewhere extra? So let's just make the 6 ohms right here. This is like an unwanted thing. See how you could measure that with your meter? You'd be like, oh, this is 6 on the bulb, but I'm getting 6 on the wire. Should you have 6 ohms on the wire? No, heck no. So is the wire good or bad? Boom, there you go. I agree. But what that would cause for amps, it would be half the amps. That would make the bulb dim. Get what I'm saying? Because it has double the ohms, so it has half the amps, so the bulb's not bright. Now let's talk about that in voltage, because we're tying them all together now. If I measured voltage right here, and this is 12 volts, we'll just make it an even number. Oh, it is 12. If I measured the voltage here, how many volts would I drop?
If the switch is on,
If the switch is on,
you can drop all of it.
I should drop all of it, but remember, I have 6 ohms here and I have another 6 down here.
Drop 12 to 6.
6.
You'd only drop 6 volts here, and where would the other 6 volts drop?
The wire.
Here on the wire, exactly. So now you're like, wait a minute. Excessive resistance on the wire equals excessive voltage drop on the wire. So the way that I test it is I measure voltage drop. If I drop 6 volts on a wire, I already know, like, that wire is no good. I should never drop more than a half a volt on any component. A wire should really be dropping like nothing, basically. 0.1 maybe. 0.01 maybe would be even better. Make sense? So the excessive resistance, which I'm going to write in now that we diagnosed it, the excessive resistance of 6 ohms unwanted causes that excessive voltage drop in a spot where it's not supposed to drop. Where should the 12 volts drop? At the load. But instead, this sibling is expecting $12, and instead it only gets 6, and it's like, where'd half my money go? Well, that's because you didn't know, but there's another sibling down here that's of equal size and strength. Make sense? So they're sharing the voltage in a series circuit. Secret family happened again. It's happened before. Make sense though? Kind of. So if you want, measure it in resistance. That's okay. It's a little more accurate though to measure voltage, but the voltage drop indicates the resistance. And the resistance measurement would predict the voltage drop. So they're kind of intertwined. Make sense? Like the secret family's intertwined and they don't know it. Okay, cool? All right, with that being said, I think you'll mostly understand where I'm going with this next activity, which is going to be I want to make sure I haven't forgotten anything, and then we're going to move on to a diagnosis. So you should be able to measure the resistance because we talked about it quite a bit. And we're going to measure it on here, so we'll be good. I was just thinking, who did I get measuring resistance? And I remembered I'm going to do it. So what I'm about to show you is a live, somebody had an interesting issue, so I was like, hold up, let's redo this. So this is going to be the board. You'll reposition me so we like it. Okay. You get it where you want it. I'm going to kill the light so it's not in my eyes. Okay. So you guys recognize this? This is the circuit that we drew. Can you read that number though? Maybe not, huh? Okay. I'm going to rework this so we can see it.
It's off.
That's true because we turned it off, didn't we? But let's go with the resistance measurement. In fact, what if I put it? How's that work? Too low?
Too low.
How about, this would have been a good thing to figure out. I could do it sideways. I can't magnet it to anything there though.
You can't like stick a.
Okay, we're gonna figure that out. Pause me for, you like it? You can read it?
No.
Ah!
It's too.
I got a pen, I got a something. How about maybe the marker? I have an eraser that won't slide. Let me see if I can rig this up somehow.
Ah, okay. Yeah.
What about up here? Too high?
No, it's fine.
Okay. If you can read it, we could do this.
We got it.
Okay. All right. First test is, first thing we're going to do actually is the customer says allegedly their brake light doesn't work. Is their brake light working?
Yes.
So I'm thinking like, how would I diagnose this brake light and if it's working? So the first things first, you guys remember way back to week 1 when we're doing troubleshooting, if it's not acting up, we don't fix it. We don't diagnose it. Make sense? So right now I'm tempted to tell the customer, there's the door. Don't let the door hit you where the good Lord split you. I don't work on something that's not broken. Like, what am I really supposed to do? Oh, what happened?
Do it out.
Oh, maybe the customer's not getting kicked out. Maybe it's an intermittent issue. So here's what we could do. Let's go with resistance because that's what we were just on. I put on resistance. You guys want to test this first wire. I could disconnect it, but I could also just leave it connected. It'd be, you know, it might not be perfectly accurate, but I can get down and dirty quick. What's my measurement? Can you see?
Yes, it says. Yes, I can see from here.
0.2 ohms?
No, 0.9.
0.9.
0.009.
Okay, 0.0. That's really good. So is this wire good or bad?
Good.
Wire's good. Let's measure the fuse. Whoops. What'd you think? What'd I get?
0.06.
You like to think that's good or bad?
Good because it's
It's good, so the fuse is good. Okay. The next, we'll measure the wire.
0.00.
Okay, so far so good.
so we're basically looking for the number point something
Well,
next to it.
it's so small. Yeah, if this is the way I think of it. By the way, what's my switch? Sunny Beach. Oh well, sounds too much. So here's the lesson. If it's a highway, would you expect to pay a couple pennies, like maybe less than a cent, right? 0.09 is less than 1 penny. I don't know. However you want to look, it's pennies on the dollar. Cool. If I'm using a road, I'm going to pay pennies on the dollar. When I get to the load, I'm expecting to spend all my $12 that's in my pocket. Make sense? A switch might be a little bit more than pennies, but it shouldn't be any more than 50 cents. Makes sense? It should never be more than, no individual component should be more than 50 cents except the load. But what's my switch?
It's open, so it's
Yeah, so when we're talking resistance is like this, like 0.1, 0.1, OL. OL means the switch is open. Is the switch open? I'll flip it. What's it now? OL. What's it now? OL. What's wrong? The switch is no good. The switch is shot. All right, but now what I'll do, I'll be thorough just for no real reason. How's my wire?
0.
Okay, great. How is my bulb? What's the bulb? What the bulb? The bulb should get something.
0.038.
Okay, so a third, 0.38 ohms. Or
No, it's 30 milliohms.
That's the load, right?
oh, it's in milliohms, so that's actually really small. So here's what I'm gonna do. I'm gonna follow my process a little bit better and do a full disconnect. What's my ohms right now? Is it really that low? I thought this thing had at least a couple ohms.
Yeah, it's 44 milliohms.
Oh wow! So that is the load. That's actually pretty low.
That looks like a dome light.
Interesting. I see 3.7 now. I probably didn't have a good connection. Can you guys see that? I don't remember if this has the backlighting.
Yeah,
I got 3.6 ohms. That I like. 3.6 ohms. Does that sound like a good bulb or a bad bulb? By the way, if the bulb was no good, this would be your reading. What'd I get?
Oh.
Yeah, so if the filament inside the bulb is broken, you get OL. Cool? So that's how you could check the bulb. If you could look at the bulb, but it's kind of like a fuse, you can measure it too. And then I could measure every wire, and the only part that was at a spec, I didn't give you the specs, but do you think a switch should be OL?
No.
So what's wrong with this car? It needs a switch, yeah. That's it. The switch is defective. We sell the customer the switch, it fixes it, and then you're kind of like, hey, I got to charge you an hour diagnosis, and the shop labor rate's $200 an hour. Like, $200 to diagnose my car? This is a ripoff, you knuckle-dragging gorillas. You know, I'd be like, whoa, settle down. We can go toe-to-toe on this diagnosis thing any day, you know what I'm saying? So a good lesson I got for you is I had a guy I worked with. I don't usually do high school, but like this dude was cool, and he and I did like an adult ed night school thing, but he taught high school during the day, and he had another teacher. I don't remember what she taught. It might have been like history or something. And she's like, oh, I'll say Mr. J, so I don't tell exactly who he is. Mr. J, can your students look at my car? And he's like, yeah, drop it off. We'll check it all out. And it was a check engine light, and it was, I believe she had a code, P0171 fuel trim lean. And, you know, class is how long at high school? I haven't been there in a while. Like an hour? An hour for one class, though. Yeah. So he's got an hour. So she drops the car off. The guys get a look at it. They scan the code. They get the code. They get to all data. They look it up. They start to barely look at it, and then they're like, class is over. So he gave it to the most advanced students he had. And so she came by at the end of the day like, hey, what's wrong with my car? And he was sort of like, we need to check it out at least another day. And she kind of like gave him some lip, like, just plug in your little computer thingy. Like, what are you hassling me for? Just plug in your little computer thingy and you tell me what's wrong with it. And this guy handled it perfectly. I mean, like, better than I could have. Now I probably handled it the same way, but I was younger then. I was a little more feisty, and I'd kind of be like, I don't really exactly know what I would have said, but it wouldn't have been probably that nice, right? So this is what he did. The diagnostic flow chart for that was like a big old stack of papers, and the students printed it. They were following the process, right? They were gathering their information, starting to execute tests. But you have to execute tests. You don't just guess on stuff. Cool? We just proved. We executed the test on this switch, and we could prove that it's the actual switch, but we did it fast. That one had a whole lot more tests involved. So he gets this big old 30-pager, slaps it on her desk, and says, bam, you read this. When you figure out because you like to read, you're more academic, you got a bigger degree than me, you read this, and when you're ready to replace a part, you tell me what part to replace. And he just walked out. And she came back the next day. You know what she said? I read that. I am so sorry. I had no idea what you guys actually do. It is step after step after test after test after test. Handled it like a boss, if I may say so. Cool. So it was, what we just did right here was a simple test, but we're testing. We're not guessing. Now let's go in another way. Here you go. What the heck? The bulb is working. How'd that happen? All right, let's do a quick test then. Now look at this. What should that switch be? Now you know why I was telling you the story. I'm buying time. What's the switch reading now? Can you tell?
039.
0.39.4?
It's 3.9 ohms.
Okay, so that's still a little too high though. So would you agree that this test right here is showing me this switch is out of spec? It's not real far out of spec. It's not like OL. Is it going down, by the way? Oh, it's solid at 3.9. So 3.9, 4 ohms, that's too much. So we know the switch is no good, but it's working though. Why is it working? But if you really notice, that bulb's actually a little dim. The reason that is, remember, the switch has contactors like this. So when the switch has a contactor like this and it makes a decent connection, the bulb will work. If it's a really clean connection, we should have like a 0.3, 0.1 ohms right there. We shouldn't be dropping a whole lot, but those connectors, those terminals, they can get burned, they can get corroded, they can get dirty, right? The switch is a really good point to start because switches has a moving part and they could fail. Now what's happened on this one, the hotter it gets, the higher the resistance goes. So right there, the switch isn't making a good connection, and that resistance makes heat. So when you have excessive resistance, it starts to make heat. The heat makes more resistance, and what's the resistance make? More heat. More resistance, more heat, more resistance, more heat. Next thing you know, it's overheated, the surface is kind of burned, and next thing you know, it's OL and the lights are up. So that's why if we were to leave this on and we can continue talking and whatever, right now this surface is heating up and heating up and heating up and heating up. What would the fix be for that excessive resistance? It's on the contacts in the switch, so we need to replace the switch. The heat is not in the male-female terminals. It's in the switch. You can't. Basically, you can't. Yeah, that's sort of what engineers would do. But as the technicians, we don't generally do that. Now it's off. See that? So if we were to measure it, there's going to be excessive resistance right now. There's been a few recalls where they have us disassemble switches and put dielectric grease and clean them all up. But I've seen people just disconnect the switch and grease up the male-female terminals and slap it together. And I know of a car that caught on fire for it. So this guy got terminated because he didn't really understand the resistance is in the terminals. The resistance is not in the terminals, the connector. The resistance is in the switch contacts. And then that resistance makes heat, and that's a problem. That's like, this is a no-go right here. That needs to be fixed. Now we'll diagnose it in another way because we talked about it. Right now, what do you think the amps are in this system, in this circuit? Okay, because we're going to summarize them, and then we're going to talk about why it's so critical. With this switch kind of messed up, switch not even working, it has very high resistance. We currently have, what do we got over there? Can you tell? It's got 0 makes sense. You know why? Because look, the light's not working. So the higher the resistance went, in this case, the resistance is what? OL. Basically, infinite amounts of resistance will cause basically 0 amps. Make sense? Now, if we were to let this cool down for a bit, which we could do, and if that light were to come back to life, which it did. Okay, so right now, you ready? Yeah, it's struggling. Oh, you know what? This probably, this might actually have did I get a connection? I don't think I got one.
Except for amps, it's fine.
I don't know, maybe that one never got fixed, so let's use this one here. I'm gonna sub out this meter, take my eraser back. Remember, we were on the whole fixing all the meters thing, but that meter was on my desk, so I might not have been able to check it. Big A.
No. You're on volts.
Oh, I am on volts. Yeah. See, I'm upside down, so I should have known a little bit. In that case, I would have blown the milliamp fuse. Yes. Not the big A fuse, though. And the other thing is, what was also nice was the switch having an infinite resistance would cause very low amps. I probably didn't blow anything. I just think I might have had it in the wrong spot. You're probably right. Okay, so if this is the case. Okay, I thought that would have done it. Don't you make me look that dumb. Okay, big A. I'm on A. Maybe this one doesn't have a good fuse. Unbelievable.
This one has a good one.
Don't even. Okay, you're sure about that one because you tested it, huh?
No, that one's fine.
Yours and. Okay. Someday I'm going to make you guys try to work upside down. Okay. Big A on A. All right, ready? You're right. It's good fuse.
There you go.
Here we go. You ready? Can you guys see our reading?
Yeah.
Watch it. 0.3. Now what?
4,
3, 2, 1.
0, 2.
Oh no. Why is it going down?
Because it's heating up.
Exactly. As the resistance is increasing, the amperage is going down. Did you see the amperage measurement as that thing died? So now you know why, right? Our resistance went up and up and up, and it choked out the amps flowing. And when the amps got so low, the bulb goes out. Cool? So we're kind of using amps to diagnose that. But now we could do one other diagnosis. I'm going to move this back to volts because remember, my go-to is volts. Right? If I put it on DC volts, I'm going to show you how I would personally diagnose this. It's not working. We'll do available voltage. I'm going to drop this on the negative. Cool. Available voltage at the source should be how much? 12. And if you guys can see, I have 12.04. Going into the fuse, what should I have?
12.
About 12-ish. Coming out of the fuse, what should I have?
12.
About 12-ish. Going into the switch, what should I have?
12.
Coming out of the switch, what should I have?
12.
But what do I have?
7.
Okay, and that number is going down as we speak. It was 4 point something, now it's 3 point something. Why am I dropping so many volts right there?
Resistor.
Right now it's actually still heating up. But I should not be dropping 12 volts. Right? I went from 12 coming in, right? What's that number?
12.
12. to 0 basically coming out. I'm dropping nearly 12 volts. I'm dropping 11.7 volts right here. Makes sense because I have 12 coming in, I have 0.3 coming out. I should not be dropping 12 volts across the switch. Ever. Never. Unless the switch is open, like it is right now. All right, so now if I give this a little bit of time to, do you see how we just diagnosed it with voltage drop 2? That was available voltage in calculating. So there's one other way we could do this. I'm gonna let it cool down for a bit, and then we'll do voltage drop. So here's voltage drop, T-Rex arms. Here to here, I'm going beginning of the wire to end of the wire. So what am I actually measuring there?
0.
Well, I mean like what part?
Oh, the wire.
I'm measuring the wire. If the wire drops 0 volts, what do you think the resistance is?
0.
Basically very low, exactly. See, so voltage drop tells me resistance, it just tells me it dynamically. All right, now I'm going to voltage drop the fuse. What do I get?
0.
About 0. Now I've been kind of trying to fool you because I was trying to save it. Okay, now I'm going to voltage drop the switch. What do I get?
6.
I'm dropping 1 volt. I'm dropping almost 2 volts. 2, 2.2, 2.3, 4, 5, 6. I'm dropping like 10 volts now. Did you see it climb?
Yeah.
You saw it was dropping a volt, and then it was dropping 2, and then it was dropping 10. You see how that was proportional to the resistance? You know what happened to the resistance? It started off low, and it got up, 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 up. It was same with the voltage drop. The voltage drop started low, and the voltage drop went up, 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 up. Okay, you think you kind of get it? So we just diagnosed this switch in 2-3 different ways. If you want to diagnose it in like a backyard, you know what I'm going to do? Ready? No meter, just brain. Not big brain, just brain. I'm going to bypass the switch. Cool? Janky, no tools, no meter, no nothing. I'm like, I think the switch is bad. Let me just bypass the switch. I fixed it because I just took the switch out of the occasion. This switch is now out. You know the problem with the customer's motorcycle, though? The brake lights are on all the time. So I do have to fix the switch, but me jumping it real quick could be like, oh, the switch is the thing dropping the volts. The switch is the thing with the excessive resistance. I'd write that up on my story, but I won't exactly say I got out my meter and I measured it, but I can write on my story, the switch has excessive voltage drop. I know it does. I know it does because I know Ohm's law and I know electricity, and I just tested it, but I tested it in a way that was fast. Can that make sense? All right, now we're going to summarize the last two things. Can somebody give me a time check?
12.
Okay, we're good. We're chilling. We're good. We're perfect because I want to drive home why we do those tests, because that's the difference between being able to fix the car and not being able to fix the car right there. And these guys got their social hour out there. That's fine. So the reason that we do these tests is because you're going to get a problem that's kind of not really make sense. And you're going to be like, well, let me test it like this. Let me test it like that. And then get an overall picture of why the bulb is dim, or of why the bulb goes out when it gets hot, or of why the bulb never worked in the first place, right? So slicing it and dicing it should have made sense. Now, here's how rust, corrosion, debris affect resistance, okay? Resistance could be measured by resistance, but you just saw we effectively measured resistance through voltage drop. Cool? Yeah. Automobiles contain 12-volt electrical system that operates various lights and control modules and blower motors and seats and whatever. All right, so we're only working with 12 volts. They receive power from dedicated circuits, so that'd be like probably the wire, but the circuit could also include the little printed circuit boards in the module and stuff like that. So that's the circuit. If you want to diagnose a horn circuit, you're not real worried about the power seats. You're looking at the horn circuit. So when we pull a diagram, you're looking at everything that's in the horn circuit, and you're pinpointing what component within the horn circuit is the cause of the problem. That's the root cause. This makes sense so far? Okay. And then generally the ground goes through the chassis. Metals corrode. Oh. Areas where the chassis is drilled or tapped, the bolts installed, and etc. are more prone to rust. So, for example, on this switch issue, this wouldn't be on the ground. Like right here, we're talking about like a ground. After the bulb, it goes to ground, right? The ground a lot of times is affixed or like drilled, tapped, and bolted into the frame, or the trunk, you know the trunk thing you open, that's called a deck lid. Now you know the professional term, you say, oh, it's the deck lid, right? If it's drilled and tapped and bolted there, and they live near the beach, like a dude I just bought a bike from, he had the rustiest '05 Tundra I've ever, no, it was newer, it was like a 2010 Tundra. It was a rot box. And I was like, why is your Tundra so rusted? I asked him point blank, and he's like, it's ocean spray. And he was in San Clemente, and I was like, you ain't that close to the water, dude. Like that thing is rot. And he's like, oh, it's from my other house in Baja. It's on the water. It gets sprayed by the salt from the waves. Like, if you have a beach thing, or up north, or in these areas where they're salting the roads, this is like a major concern. Like, this is all the time. Southern California, a little more spoiled, you know. We don't really have rust corrosion issues typically on the grounds, but it's a really big deal in some areas. Okay. And if it is corroded, it causes higher resistance. Remember, we just saw it. So that switch, remember how the resistance went up and the light bulb got dim, 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 and then went out? It could be the switch, but it could also be the ground bolt. It could also be a wire, especially if a wire got the insulation pierced and a little bit of corrosion gets in there, and that little bit of corrosion's like a cancer, right? It gets more and more and more corroded. Next thing you know, it's got high resistance. It could cause that exact thing. So I just described 3 situations that could cause that issue. Are we replacing a switch? Are we replacing a wire? Are we replacing a ground? I don't know. We have to measure, we have to diagnose. Make sense? Locating excessive voltage drops caused by resistance by performing a voltage drop test from the battery positive to the feed side of the circuit. Okay, do you understand that? We're locating high resistance using voltage drop test. And that's what we talked about actually last week. Remember, we were measuring voltage drop. So the wires should drop like point nothing, very little. The switch might drop a little bit, no more than 0.5. And then the load should drop the whole thing. But if you see a component that's dropping more than 0.5, that's dropping excessive voltage. That means there's excessive resistance. And you didn't even measure resistance. You implied the resistance by the voltage drop. Cool, make sense? All right. And then what that could look like, well, maybe it's an eyelet like this. This is a ground. We have to unbolt it, pull it off, clean it with a wire brush, maybe clean it with a, it's almost like if you're washing pots and pans, you know how you can use the scrubby side and it really scrubs it off? You could do that. You could use a little grinder on a whiz wheel, clean this up. One thing that I've seen is you guys aren't real passionate about fixing customer. Yeah. You guys aren't real passionate about fixing customers' cars. Like, who really wants to work on a 2022 Camry? All right, nobody really wants to do that. But look, there's a lot of people with Camrys, and those Camrys need to be fixed. Those people need to go to work. They need to be productive members of society. They need to go to a job. They need to trade their time for money and an agreed upon amount. There's millions of people who just want to do that. If what you really want to work on is some custom hot rod thing or whatever, cool, but most of the people who want to work on those do it. They don't pay somebody else to do it for them. Okay, you understand my point? So in the unlikely event that somebody hires you to do like a full frame off restoration and you pull the whole vehicle apart and then you powder coat all this stuff and you do like a high temperature paint on the engine and you do like some sort of epoxy on the frame and then you bolt this up, what do we do to the frame? Epoxy painted it. If you don't clean bare metal right there, if this gets bolted down to paint, that won't be a good ground. Makes sense? You want to know this type of stuff kind of going into it, like anything that could cause excessive resistance, paint, rust, these types of things, we'd have to clean all that up. Cool? This harness right here, it's a little bit hard to see, but I'm actually going to dim the lights. It's worth it. This harness right here was a rub. So if you look, this was chafing. It's like called chafing. If you don't know what chafing is, you're going to find out someday. So if this was chafing against something, it scraped the insulation off. Now you see the little copper wires in there? What do you think that's going to cause?
Oh, kind of stuff.
All right, so this one was resistance if it was corroded. This one is going to be resistance, but what if this is chafing against bare metal that's a ground? That would be a short, right? So if we short out some of these positive wires, that's blowing a fuse. But if we chafe them against maybe something plastic, that's not a short, but it scraped the insulation, which means now it's going to start to get corrosion. Some of these actually might already be open. If they're completely cut, that's an open. But if they're like, if there's 30 wires in this strand and 29 of them are peeled off, technically it wouldn't be an open. It would actually be a high resistance. I mean, remember to shut these meters off. Cool. So these are types of problems that we see. Another thing that could look a little bit like this is when the mice be chewing on that stuff. They'll be eating this part. They'll just pick a wire. They'll be like, oh, blue, love blue. It's like you when you go get the, like, you know, freeze pop is. What do you guys call them? A popsicle? What one you want? You like blue? I like blue ones. The mouse will just be like the blue one, an Otter Pop. The mouse will be like blue wire. I like the blue one. Why the blue one? I don't know. It just chews the wire it wants. And then it'll sometimes chew a section out. It's a whole big old mess. And that might power something. What's it power? I don't know. It's going to power some component, something, some whatever. Cool. So right here you have 5, 6, 7, 8 damaged wires. What the customer has though is a check engine light and this warning light and this concern and this whatever. And so they don't come in and say like, hey, the mouse chewed my wires. They come in and they say, my headlights don't work, my red brake light's on, and my check engine light's on. And you're like, oh. Then next thing you know, you start doing your investigation, you find this. And then you find this one is for the parking brake, this one is for the O2 sensor, and this one is for, what was the other thing that didn't work? Whatever. If the power seat doesn't work, this one powers the power seats, right? So this is some of what we do. We find this type of crap. Cool. And then again, we can, if it's a ground eyelet, we can clean those up. Cool, we could do that. We've got to clean it all up, wire brush it. You can use electrical contact cleaner. Baking soda does work. Coca-Cola does work. You could use quite a number of different things, but at the end of it, it has to be clean, and you should actually be able to verify that with a resistance measurement or a voltage drop measurement. You can verify it. Cool, clean up. Now, if you have wires, we're going to get all into wire repair, okay? So bear with me. But if the wire has excessive resistance, that's got to be repaired or replaced. You can replace the wire. If it's a switch, we replace those generally. There are some people who will take them apart and clean them, but that's not real normal. Especially, you know what's really common? The driver's window, the master switch they call it. You know why those are mostly a problem on smokers' vehicles? If it's ash could be some of it, but when the customer's smoking, it's rain outside, what's the status of the window? Window's down and it's raining outside and it gets corrosion, it gets a little water, it gets a little more, right? So like sometimes I use external factors. If I hop in the car and it's got the black ice Christmas tree and it's smelling like they definitely been smoking, but they're trying to cover it up and the windows don't work, I may skip testing the fuse for the windows. I may be like, I'm going right for the switch because I think that's what it's going to be because I know they be smoking. Make sense? You're allowed to do that. Is it profiling? Probably. But if you find the problem quicker, you're not writing anybody a ticket or nothing. You're trying to help them. You're trying to help them. So it's okay to profile them when you're helping. Okay? Now with that being said, we replace the switch or whatever. If it's the male-female thing, if those are corroded, generally, those are really hard to clean. You could try to clean them, but like the rust gets deep inside that terminal, and if you try to clean it, you mess it up. If it's a connector, we're probably going to replace those. You can actually a lot of times get an end of a connector called a pigtail, cut that whole thing off, attach a whole new connector. You probably get the male, probably get the female, right? Health class, if the male's got issues, now the female has issues. So, you know, if you get a brand new male and it's with, now they got issues again, you make sense, just start over. Okay, let's keep it professional. If they're damaged, cut male and female off, get new connectors. That's not a comeback. Whereas if you kind of fix it, this is the thing, you could try to save the customer so much money and be like, I'm gonna charge no money in parts, I'll just clean this really good. That's nice, but when it's professionally, if you fix it, you charge them and it breaks again in 28 days, That's not a good business. They're going to come back and you're going to have to fix it for free this time. And now you're like, you know what? I need to replace them. And they're like, you already charged me once. I'm not paying again. And now somebody else is paying. You're eating the cost. So like our repairs need to be long-term. For male, female terminals, we don't usually fix those. But for eyelet, yes. Right. And so sometimes we can have corrosion that causes intermittent. So if we have an intermittent issue, sometimes wiggling can help us find the corrosion. Sometimes if it's like if it's a wire and the wire's got some corrosion and I can see the light bulb's on, let's say I move the wire, it's on, I move the wire, I get down to here and all of a sudden I move it and it flickers. What's that tell me? Probably then I'm going to get more surgically involved and be like, oh, there it is. You know, so like these are good tricks on the car, pretty common. Another thing is road debris. So anybody ever hit something in the road? I mean, it's going to happen. If it hasn't, it will. Sometimes those road debris will go up and actually hit a harness, cut a wire. Real common to have an ABS light on. If a car comes in with an ABS light, you know the first thing I do? I look to see if the fender liners are there because a lot of times they hit something and it rips that plastic liner out and it rips the wheel speed sensor harness. It's like, it happens all the time. So rather than getting my meter out and being really technical, I just be like, wheel speed sensor code. I wonder if they hit debris, and I'll look and it'll be right there staring at me, all ripped up. Make sense? So, but that's still going to be maybe an open. Pretty common. We could test those with voltage drop or resistance. And so I think this overall, I think you'll understand because this is what we just did on the switch. If let's say the switch was defective, what's that? If that switch has excessive resistance, what's it cause for our amperage? Who knows? Amperage.
It goes up.
If the switch has excessive resistance, don't make me pull up that picture. You know the guy with the ohm, right?
Oh, it tightens it.
He tightens it up so the amps go down. Cool? So if you have excessive resistance here, your amps are going to be low. If you have excessive resistance here, and we were to measure here, what would your resistance be?
12.
Well, we don't know the number, but let's say if your resistance is, if you have excessive resistance here, what's your resistance number going to be? More or less? More resistance means more ohms. Cool? But let's say that if you have excessive resistance here, what would your voltage drop be here? That's what I'm saying. You have more resistance on the switch. What's your voltage drop across the switch going to be? You don't know the number yet, though. Just tell me more or less. If you have more resistance, more voltage drop or less? Less would be great, except that's not how it works. If you had if you had more resistance here and you had less voltage drop, that would mean this bulb would glow extra bright because it gets more voltage drop for itself. But that's not how it works. So if you have resistance here, is this bulb going to be bright or dim? Dim, which means we're dropping voltage here more than we should, and we're dropping voltage here less than we should. Makes sense? Because they have to share it because they're in series. And so it's a little bit of a tough concept, I'll admit, but you want to get all this stuff kind of worked out in your mind. Resistance drops your amperage. Resistance in a component will raise the voltage drop in that component. But in the law of electricity, we will always drop the source voltage by the time it gets to ground, okay? So if it's 12 volts from at the source, we're going to drop 12. If there's excessive resistance here, this is going to consume some. It's going to leave less for this one. But it will always drop the source voltage, 12. 12.6, whatever your number is. Okay, kind of make sense? It's a little technical. I think you can get it. I think overall you guys are probably pretty good on the resistance. Yeah, rocking. And then a diode check is super easy. You guys have done that a couple times, but just because that's the final measurement. If you need to do a diode check, yes, put it on diode, measure this way, flip it. One way it should flow, like this. Flip it. This way it should be OL because it won't flow. And now, yes, we're done. Tim, if you can go ahead and hit the full stop button. You think you